So what I wanted to talk about is, often as a chemist, I get the question is, what is the most important reaction in chemistry? And these are some of my favorite things, is when I get these questions, because they lead me to do investigations, and inevitably they lead to some of the more fascinating stories that I have. So I'm going to talk to you today about the reaction that saved the world. So one reaction is actually that important. So where the story starts is about 150 years ago, and this is a question that I had for myself, is I would hear about famines, and the idea would be that there's land, and there's water, and there's seeds, but I wouldn't understand why is it that people couldn't grow food inside of there. So 150 years ago, this was a problem where people would have land and not be able to grow food. And me personally, I wouldn't understand why this was being a problem. So what happens is, as you grow crops, the plants need nitrogen to grow and to build themselves. And as you plant crops inside the ground, they pull nitrogen from the ground, but they're not able to put the nitrogen back. So if you keep growing crops into the same location for too long, you actually will leach all the nitrogen out of the ground, and the ground will become fallow. So it will nothing will grow. So the only real way, so about 150 years ago, the only real way to put nitrogen back into the soil was cow manure. And the problem is that cow manure is actually kind of hard to get, and there's just not enough of it to feed the whole world. So this is why, about 150 years ago, so many people were starving. So if you think about it, it's kind of an odd idea that the ground is starving for nitrogen, but our atmosphere, about 80% of it is made out of nitrogen, or N2. And so this is kind of a curious idea that we're surrounded by nitrogen, but yet we're not able to use it. And in reality, only about 1% of living organisms can actually use the nitrogen from the atmosphere and put it into their bodies and use it to make the building blocks of life, which is like protein and DNA. So this is, in order to do this, it has to undergo what's called a process of nitrogen fixation. So taking this N2 molecule and turning it into another type of nitrogen that most living organisms can grab and turn into the building blocks of life. And so that 1% is generally the small nitrogen fixing microbes. So in particular, legumes they have these little microbes inside of their roots. So you might have heard of doing things like crop rotation. So there's certain crops that you can actually grow inside of the ground, and it will put nitrogen back into the ground, and then you can come back and put a different crop inside there. So up until the early 1900s, really, if you wanted to grow crops, you had to either put cow manure or put certain kind of crops inside of there. But overall, getting nitrogen into the ground was a problem. But so this leads into the question, so what's so special about N2? Why is that such a problem to take it and turn it into something that's usable by living organisms? And it has to do with this triple bond. So nitrogen that's inside the air is actually in triple bonded to N. The problem is this triple bond is one of the strongest bonds known, which means it doesn't want to break. It doesn't want to turn into something else. And in this sense, this makes nitrogen gas very inert, which is very good for our atmosphere. Our atmosphere is very inert, and if our atmosphere was made out of pure oxygen, the first time somebody lit a match, the whole planet would go up. But the idea is we're surrounded by nitrogen, but up until this reaction I'm going to talk about, we haven't been able to utilize it. So the story really starts with this gentleman, Fritz Haber, who was a German chemist. He actually received the Nobel Prize. But one of the things I want to mention for how important this reaction is. So this gentleman actually has literally saved the whole planet. Almost nobody has ever heard of Fritz Haber, and it's kind of for a good reason, and we're going to talk about it here in a little bit. So what Haber developed was what's called the Haber-Bosch process, and he actually developed an industrial reaction where you take nitrogen from the air. So we have like this unlimited supply of nitrogen, and he would actually just take hydrogen from the air. There would be a catalyst, and he would be able to take it and turn it into ammonia. This ammonia is now fixated, or it's able to be used by living organisms, so with a little bit more development. So what's kind of funny, though, even though that this is going to be used for different things, at the time, really when they developed this process, one of the first things they used it for was to make munitions for Germany during World War II. So what happens is in order to make explosives, you need what's called nitric acid. So in order to make this molecule TNT, one of the basic explosives, which was one of the main explosives that was needed during World War I, you need nitric acid, and one of the main ways of making nitric acid is by taking nitrates and dissolving them in the water to make nitric acid. And if you take this molecule toluene, you react it with nitric acid, you make TNT. So if you have nitrates, you can make TNT. And with the Haber process, remember the Haber process makes ammonia. You can take ammonia, turn that into nitrates, and then turn that into nitric acid, which you can make into TNT. So why did they want nitrates so bad during World War I? So the idea here is that before the Haber process, the only place that you could get nitrates in the whole world was off the coast of Chile. So off the coast of Chile, there's this trench. So it's a very deep water trench, and inside of here, there's microbes inside of here that would feed off the nutrients and actually do nitrogen fixation inside of the water. And then the fixated nitrogen would get blown into Chile onto these deserts, and it would form pockets of nitrates. So what happened before the Haber process, if you wanted to make nitric acid to make munitions, you had to go to Chile to get the nitrates and turn it into nitric acid and then turn it into TNT. But the problem is, remember, during World War I, Germany was fighting England, and England had control over the ocean. And so Germany was separated, so Germany could not come to Chile to get the nitrates, and they were cut off. So they had to come up with a different method for making nitrates to be able to make TNT. So with this, after World War I, one of the other things that they figured out is that one of the another really good use for ammonia, which comes from the Haber process, is you can use it to make fertilizers. So one of the main fertilizers that we have, so we know the Haber process makes ammonia. We also know that we can make nitric acid from the Haber process, from ammonia. You mix those two together, you make ammonium nitrate, which is one of the primary fertilizers. So this is really what we're getting into, is that the Haber process allows us to make fertilizers. And with this, in combination with pesticides, it was more than just being able to add fertilizers to the ground. We needed pesticides. Those combination of those two, so now we're not limited by cow manure and legume microbes on legumes. That's quadrupled the productivity of the agriculture. So the idea here is, if we try to sustain the world at where we were at the year 2000, it would take nearly 4 times as much land as what we're using right now. So to put this into perspective, if we wanted to feed, without the Haber process, if we wanted to feed everybody on the planet right now, it would take nearly half of the ice-free continents. So nearly half of the land on the planet would have to be used for agriculture to be able to feed everybody on the whole planet. With the Haber process, so by combining the pesticides and the fertilizer, we really only need about 15% of the land. So you're beginning to see how important this reaction is. So also to give you an idea of how important this reaction is, so we actually, the Haber process produces about 450 million tons of nitrogen fertilizer per year. To give you an even better idea, about 1 to 2% of the world's annual energy supply, so all the energy that's being produced by the whole planet, about 1 to 2% of this is going into the Haber process to be able to make fertilizers to be able to feed the world. So one of the things that came from this now that food is not a problem, the Haber process has actually been called the detonator of the population explosion. So now people are not starving, and feeding people is not a problem. And so what happened is globally, this caused our population to just go rampant. So we went from about 1.6 billion in 1900 to about a little over 7 billion today. So when we look at this graph, so this is about where the Haber process came in, you can see that the world population shot up because we had enough food for everybody, people stopped starving. But which is typical though, when human beings get involved in natural processes, there's kind of ramifications from it. And one of the other things that you can see here is this line represents the total amount of nitrogen that's inside of the environment. You notice that has shot up too. So by using the Haber process, we're putting an unnatural amount of nitrogen into our environment. So what kind of ramifications is that causing? So what happens is, and just to give you the last idea, how important this reaction is, that if we didn't have the Haber process, nearly half the world's population, about 3 billion people, would be starving. So that tells you how important it is. And in short, if we didn't have the Haber process, we would already, our planet would be overpopulated. Okay, so really this is the reaction that saved the whole world. Without this process, we'd have already reached overpopulation. So one thing I always like to put something in there to try to shock people, how important, and another idea about how important this reaction is, it's been estimated that nearly 80% of the nitrogen inside of our bodies came from the Haber process. So if you think about it, when we look at DNA, there's a lot of nitrogen in DNA. Much of the nitrogen that's inside of your DNA actually came or was made from the Haber process. That's how important it is. So and if that's a problem to you, one of the things that's kind of interesting, that in order for a food to be labeled organic, they have to use fertilizers that were not made from the Haber process. So in order for it to be an organic food, they have to use manure or some other nitrogen source. But this is how important this reaction is. Nearly 80% of the nitrogen found in your tissues has come from the Haber process. So as like I was saying, so it's unfortunately now we're putting too much nitrogen in the environment. So what's happening there? And of course, it's going to be something bad. So the idea here is plants don't use all the fertilizer you put into the ground. So about 50%. So of the fertilizer put into the ground, about 50% of it is used by the plants. The rest gets washed down. So the fertilizers are water soluble, and it undergoes leaching. So when the water runs through it, the fertilizer gets moved down the water table and into the ocean. And so what we see is I fertilize land. The plants only use about 50% of it. That gets leached into rivers, into estuaries, and then eventually into the ocean. So now all of these water supplies are over nitrogenated. And what do we end up seeing is what's called eutrophication. So inside of here, we have algae, and the idea is the algae is used to only having a certain amount of nitrogen. Now we're putting too much nitrogen inside of the waterways. The algae grows too much, and it creates what's called dead zones inside of here. So what happens is the algae ends up blocking out the sun and killing off fish and other living plants. So it's a big problem. So if you're ever by an agricultural center, so I got my PhD from Davis, which is known for being agricultural, I would see these green kind of pockets inside of there where the fertilizer would leach into the sort of the creeks there. One of the other problems is that our nitrogen fertilizers gets react with microbial nitrification to become nitrous oxide, which is actually a greenhouse gas. So the Haber process, or over-nitrification of the land, is actually helping to cause global warming inside of here. So if we look at it, about half of the man-made nitrous oxide that goes into the atmosphere comes from the Haber process and over-nitrification of land. So why have you never heard of Haber? So if we see this, hopefully I've proved to you that Haber and the Haber process is very, very important. So why have you never heard of Haber? And so this goes back to World War I. So during World War I, Haber was a fanatical German patriot. He was a chemist, and Germany was losing the war, and they came to him and said, can you help us win this war? And he was the one who had the idea of using chemicals to kill the other troops. And so there was one incident where he used 498 tons of chlorine gas to kill over 10,000 French troops in one incident. And so he has been named the father of chemical warfare. And he was actually, after the war, he was called a war criminal by the Allies. And the idea is they didn't persecute him for this, probably because he was a Nobel laureate and it would have looked bad. And then kind of in the sad note, prior to World War II, because he had a Jewish heritage, he actually was exiled from Germany, and he was forced to live in Switzerland, where he ended up dying. So this is one of the stories that's inside of my book, Strange Chemistry. If you want more, please take a look at that, and thank you for listening.